Hello friends, my name is Prashant Kumar. I am TA for this course. Till now in this course you have learned about phugoid mode, longitudinal dynamics, lateral dynamics, short period mode, spiral, Dutch roll and roll modes. Today I will be emphasizing more on the numerical part of that. So before continuing on to numerical, let's see what were the dynamics equations which we derived for longitudinal as well as for lateral mode. In previous lecture you might have seen the longitudinal matrix was given by XU. This is a matrix of longitudinal dynamics mode. Now in longitudinal mode there are two modes, short period mode and a phugoid mode, and the approximation matrix for those are, for phugoid mode the matrix will be given by XU minus G minus ZU upon U naught 0. So this is a matrix for phugoid mode. So characteristic equation for this phugoid mode will be psi minus A equals to 0. Now equating this matrix will get S minus XU G ZU upon U naught S equal to 0. So the characteristic equation will be S square minus XU of S minus ZU G upon U naught equals 0. From this characteristic equation we can see that the natural frequency for phugoid mode will be under root of minus ZU G upon U naught. Similarly, we can derive the value of zeta from this equation, that is zeta will be minus XU divided by 2 of omega n p. Now, this was a natural frequency given for phugoid mode. If we neglect the compressibility effect in phugoid mode, the natural frequency formula reduces to neglecting compressibility effect, omega n for phugoid can be written as root 2 G upon U naught, and the value of zeta will become 1 by root 2 1 upon L upon D. These all calculations you have seen in your previous lectures. I am just repeating what were taught in that previous lecture. So this is for phugoid mode. Now we will be seeing for short period mode. For short period mode, the matrix was given by W plus dot ZW U naught MQ, this is Q, M of omega dot into U naught. Similarly, the characteristic equation for this short period mode will be S square minus MQ plus alpha dot plus Z alpha upon U naught S plus MQ Z alpha upon U naught minus of m alpha. Now you might have noticed I have written m alpha dot and m alpha instead of mw. That you can easily derive since you know that alpha is given by w upon u. So that's why you can replace w by alpha into u. So when making this substitution in our equation, you will come to this characteristic equation. So from this characteristic equation, we can see the natural frequency for short period mode will be under root of mq z alpha upon u naught minus of m alpha, and zeta will be mq minus of mq plus m alpha dot plus z alpha on u naught divided by 2 omega n of short period mode. So up to here, this all were taught in the class. So this will be the formulas we will be using in numerical, which I am going to write out now. So let's take a numerical on a longitudinal mode. Using this longitudinal derivatives, you can directly substitute these variables in this equation and you will reach this longitudinal matrix. Characteristic equation of this longitudinal matrix will be derived from the same formula as we did for short period and phugoid mode, that is Si minus A equals to 0, where A is the longitudinal matrix. Now since you know this is a 4 cross 4 matrix, so the order of the characteristic equation will be of the 4th order. So let's derive the characteristic equation using this formula. The longitudinal mode characteristic equation will be determinant of S plus 0.045 minus 0.036 0.3212 0.369 S plus 2.02 0.0396 minus 176 S plus 2.948 0 0, this will be minus 0.0019 0 0 minus 1 S. So determinant, equating this determinant to 0 will get characteristic equation. So it will be pretty long calculation, you have to bear with me. Since you know this is a 4 cross 4 matrix, so what will be my best strategy is to go for minimum calculation. So I will be choosing this element and this element, because like that I have to only calculate the determinant of 2 sub matrices. So I will be taking this, and the general formula for calculating determinant of any matrix will be that element minus 1 to the power of what is the location of that matrix, that row and column, sum of that. Since this is a 4 cross 4 matrix, this is 4 cross 3 and this is 4 cross 4. So sum of the position of rows and column, that is 4 plus 3, then determinant of the matrix remaining by eliminating the rows in which that element is there and column in which element is there, that is determinant of this matrix I have to calculate, that is S plus 0.045 minus 0.036 32.2 0.69 S plus 2.02 then 0 minus 0.0019, 0.0396 and 0. This then plus S, and same using that formula minus 1, 4 plus 4, and determinant of the matrix by eliminating submatrix, eliminating the row and column which the element lies. It will be this whole matrix. S plus 0.045, 0.396, okay, minus 0.0019, minus 0.036, S plus 2.02, 0.0396, 0 minus 176, and S plus 2.948. Now for solving this equation we will get this will be minus 1, so it will be 1, and determinant of this submatrix will be S plus 0.045 into this eliminating 0 into 0, 0 minus 0, minus of minus, that will be plus 0.036, and eliminating there is 0 minus 0. So we will be left with only 32.2 and 0.369 into 0.0396 minus of minus, and minus will be plus 0.0019 into S plus 2.02, okay, plus S, and this will be the determinant of submatrix, which will be S plus 0.045 into S plus 2.02 into S plus 2.948 minus 0.0396, minus and minus will be plus into 176, minus minus plus 0.036 into 0.369 into S plus 2.948 minus of 176 into 0.0019. So this will reduce to 0.061 S plus 0.593 plus, equating this part will get S into S cube plus 4.968 S square plus 12.92 S plus 0.045 S square plus 0.223 S plus 0.587 plus 0.013 S plus 0.027. Which will be further reduced to S power 4 plus 5.05 s cube plus 13.2 square plus 0.67 s plus 0.59 equals to 0. So, this is your characteristic equation for that longitudinal matrix. So, I will be showing you how to calculate the roots of this characteristic equation or higher degree polynomial. But before that, we already derived the formula for short period mode and long period mode. Let us see what are the roots for the short period and long period mode. For phugoid mode, we already wrote that omega and phugoid will be root over minus ZU G upon U naught. Okay, I didn't mention. U naught is 176 feet per second. Okay. U naught. So, it will come around 0.26 radian per second. Similarly, value of zeta will be minus xu upon 2 omega and phugoid, which will be 0.087. Similarly, for short period, omega and short period will be root over z alpha m q u naught m alpha, which will give 3.6 radian per second. And similarly, zeta for short period mode will be 0.69. I am not doing the calculation, just you have to substitute this value in the formula and you will get that value. Okay. And the characteristic root for this equation will be, I will show how to derive this afterwards. The characteristic root will be equals to, since this is a fourth order equation, so we will get 4 roots, that too complex conjugate poles. S12 equals to minus 0.0171 plus minus 0.213 I, and S34 will be minus 2.5 plus minus 2.59 I. Okay. So, these were the roots derived for characteristic equation of fourth order. From approximation, roots will be given by minus zeta phugoid omega phugoid plus minus omega n root over 1 minus zeta phugoid square. Similarly, for short period approximation, the roots will be given by minus zeta short period omega n short period plus minus omega n short period root over 1 minus zeta short period whole square. Now, for phugoid mode, if you calculate the value of t half, which is given by 0.69 by eta, okay, where eta is the real part of that root, will calculate to 6.09 divided by 0.0171. This is for the characteristic equation, the roots which got for characteristic equation. What will be the value of t half? It will be, this is mode, so this will be equal to 4t.3 seconds. Similarly, t half for short period mode will be divided by 2.5 which will give me 0.28 second. These were the t-half we got for characteristic roots we got from characteristic equation. Now, for the roots which we got while approximating phygoid and short period mode, from that t-half will be t-half phygoid mode equals to 0.69 divided by 0.023 equals to 30 seconds. Similarly, for t-half for short period will be 0.69 divided by 2.48 equals to 0.278. You can check that by calculating the value of short period and phygoid mode approximation. Just substituting the value of zeta and omega n, you will get the value of roots what will be for phygoid and short period mode. Now, as you can see, the exact root gave me a t-half of 40.3 seconds, while during approximation for phygoid mode I got t-half as 30 seconds. As you can see, the t-half which I got from exact root analysis was 40.3 seconds, and the t-half which I got for phygoid mode during approximation is 30 seconds. This gives an error of about 25%. While for short period mode, the error is very minimal, or you can say the approximation was very accurate. So, now coming back to how to derive the exact root of this fourth order polynomial or higher order polynomials. For that, we will be using a numerical method known as Newton-Rapson for calculating roots of higher order equations. Newton-Rapson method's numerical calculation works on the formula given by xn plus 1 equals to xn minus f of x divided by f dash x, where fx is your polynomial for which we have to derive characteristic roots, or we have to derive roots. F dash, as the word is clear, this will be a derivative of this polynomial. Now, this n is your previous value, and what will be the value you get from substituting this value in the function. You will get next value, and you substitute till you reach your solution converges, or you reach a tolerance value. For instance, I have given my tolerance value as 0.001. So, when this tolerance value is reached, my difference between the previous value and the next value is within the limit of 001, my solution will converge there. So, I will show you how to find roots of the characteristic equation, that is fourth order longitudinal matrix. So, my function fx will be given by S4 plus 5.05 S cube plus 13.2 S square plus 0.67 S plus 0.59. Now, differentiation of this f dash x will be 4s cube 15.15 s square plus 26.4 s plus 0.67. Now, using Newton-Rapson method, that is xn plus 1 equals to xn minus f of x f dash x. Now, there is one limitation to Newton-Rapson rule. If you know the roots are in complex plane, you have to give initial value as a complex number. Otherwise, if you give it a real number, the solution won't converge if your characteristic equation contains only complex roots. So, solution won't converge and it will continue to run for an infinite loop. So, that is why if you know that your solution contains a complex root, so better give the value of xn as a complex number. Since we know this is a fourth order polynomial which consists of two roots, both complex and conjugate. So, suppose this initial value of n I will give x naught equals to I. Let us see what will be the value of this Newton-Rapson where it converges for the value of x naught equals to I. So, for x naught equals to I substitute this value of I in my equation f x and f dash x to get the value of this numerator and denominator, which will be subtracted from x equals to I. This gives me for first iteration x dash will be equal to minus 0.1056 plus 0.5528 I. Now, substitute this value, the new value of x in this in the equation of Newton-Rapson. So, now xn will become the value which obtained after iteration 1 and the new value of xn plus 1 will be after second iteration, it will be again repeating the same process. This will be I, fourth iteration, zero 0.0166 plus 0.2121 I, sixth iteration give me minus 0.0170 plus 2125 I, seventh minus 0.0170 plus 0.2125 I. Now, as you can see, after sixth iteration, solution of this equation will have the same value, this value will be repeated. So, we can say the root of this characteristic equation, or we can say one root of this characteristic equation will be 0.0170 plus 0.2125 I. Now, since we know these are fourth order equation, it will have four roots and all the roots will be conjugate of each other. So, there will be same root with a mirror image of this root, that will be minus 0.0170 minus of 0.2125 I. You can verify this by putting the initial value of x naught as minus I. The root will converge at that particular point. Now, this was for the first root, means, or you can have pair of root. Now, if you want to derive the second root or the second conjugate root, you have to change the initial value of x naught to some higher value, because the Newton-Rapson rules will converge to the nearest nearest root. So, if I give minus I or minus 2I, it will continue to converge to that particular point, so you won't be able to get second root. To get my second root, let's take the value of x naught as minus 3 plus 3i. Now, for if you give initial value as 3 minus 3 plus 3i, your Newton-Rapson will give solution as x dash for first iteration will be minus 2.6683 plus 2.674i. This is first. Second iteration will give minus 2.5274 plus 2.5879i. Third iteration will give x dash equals to minus 2.5080 plus 2.5870. Fourth will give x dash equals to minus 2.5080 plus 2.5972i. So you can see as the roots are repeating, so we can say this is another root of the equation. So this is one root, then we have a mirror image of this. So another root will be same with the minus sign. So we can say these are the roots, or you can say these are the exact root of the characteristic equation given by this polynomial. Previously you saw the characteristic equation of longitudinal mode. So now we are doing a problem on lateral mode, and here also you know the lateral matrix is given by this derivative formula, this formula matrix, and the roots of lateral direction characteristic equations are spiral roll and Dutch roll. The roots for different modes are, for spiral mode it is given by L beta nr minus nr n beta divided by L beta. Similarly, for roll it is LP. For Dutch roll you can get the roots by solving the characteristic equation minus y of beta plus u naught n of r by u naught plus y by beta n r minus n beta y r plus u naught n beta whole by u naught. This is for Dutch TCH. These are the roots for various modes approximation. This will be the roots given for spiral roll and Dutch roll modes. So based on this, let's see a numerical. The matrix for lateral dynamics is given by this equation, and various lateral direction derivatives are mentioned here. So first of all, what you will be doing, will be finding the characteristic equation for this matrix, and as we know, the characteristic equation for any matrix is given by Si minus C, determinant of this equals to 0. Characteristic equation we will get S plus 0.254 1 minus 0.182 16.02 S plus 8.40 minus 2.190 minus 4.488 0.350 S plus 0.760 0 minus 1 0 S, determinant of this equating to 0. So for my convenience, or you can see the calculation will be easy if I choose this element and this element, because I have to deal with only two submatrices. So we will get quadratic equation as 0.254 1 minus 0.182 16.02 2.19 minus 2.19 0 minus 4.488 s plus 0.76 0 plus s minus 1 to the power of 4 plus 4 and determinant s plus 0.254, this is 2, 0 1 16.02 s plus 8.40 minus 2.19 minus 4.488 0.350 and s plus 0.76. Now I won't be doing the full calculation, just do the calculation, and the final matrix which you will get for this LA known as the characteristic equation for lateral directional matrix is S4 plus 9.417 S cube plus 13.982 S square plus 48.102 S plus 0.4205. So this is a final characteristic equation for the given matrix. And now if you want to calculate the roots of this characteristic equation, or the exact roots, we will be using the Newton-Rapson method, which you have already seen. Now the approximate solution or approximate root for this matrix will be given by these approximate roots for different modes. So equating this using the derivatives given for these questions, the root for spiral mode will be minus 16.02 into minus 0.76 minus 2.19 into 4.49 divided by minus 16.02, which will be equal to your minus 0.144. Similarly, for roll mode, it will be simply LP, and LP is given as minus 8.4. Similarly, for Dutch mode, you can substitute the value of y beta and every derivative from the equation, and the roots for this equation will be lambda 1 2 equals to minus 0.51 plus minus 2.109 I. Now using this equation you can calculate the natural frequency and the value of zeta. Now what I am interested in, what will be the values I will use so that this series converges very quickly. So the trick for that part is, since approximation of these modes are very easy, so keep the value of the initial values in the Newton-Rapson formula, which we already mentioned was n plus 1 equals to xn minus f of x by f dash of x, where fx is a characteristic polynomial for which we have to determine the roots, and f dash will be simply derivative of that, Let me write the f dash value of this also. F dash, this will be f of x. F dash x will be given as 4sq plus 28.25 s square plus 27.96 s plus 48.102. So this is f x, this is f dash x. So I was telling you the trick part, or you can say what should be the value of this xn so that my series converges very easily. So for that, as you know, you can the approximation for modes are very simple. So just use these values as an initial value. So your series will converge with minimum number of iterations. So let me show what will be the value for different, if we substitute these values in the initial value of this Newton-Rapson formula, how many iterations it will require to reach a convergence. So for instance, since there are 3 roots, and as you know that for a single root, just change the sign of this in the initial value, you will get both the root. Let me show you how many minimum iterations are required for a series to get converged. So let me put x equals to 0, x naught equals to 0. See, since my first root is very close to 0, so substituting this value in this function, or you can say fx and f dash x, my value of x dash will be minus 0.0087. This is first iteration. After second iteration, now substitute this value in place of xn and you will get x dash is equal to minus 0.0088. Third iteration, minus 0.0088. So you can see, just by putting the value of 0, my iteration has reduced. Just after 2 iteration, I get a root of the equation. So this will be the exact root for your spiral mode. As you can see, the difference between calculated by using approximate formula and the exact root which you got from the Newton-Rapson method. That's why the approximation for spiral mode is not very accurate. So as you can see, by putting the value of x naught, my series converged in 2 iterations itself. For second root, now let me put x naught equals to minus 10. You can put minus 9 or minus 8, it will converge very fast, but let me put minus 10. My first iteration will give me minus 8.933. Second iteration will give minus 8.505. Third iteration will give minus 8.436. Fourth iteration will give minus 8.434. Fifth iteration minus 8.434. So you can see after fourth iteration, I got the value of root, what will be the exact root of the characteristic equation. So the more closer you put initial value to your approximate root, the minimum number of iterations it will be required to reach the exact root. So my suggestion is that if you have already calculated the approximate mode, just give that initial value close to that value, you will get the exact root. And similarly, since you have got these 2 roots, the third root will be for this Dutch roll. As I already mentioned that the limitation of this Newton-Rapson rule is that if you give it a real number, it will always remain in real domain and your series won't converge if it has a complex root. So better give your roots in terms of complex number, then your series will be giving you the exact root of that equation. Number of iterations required to reach third root. Let me put x equals to minus 1 plus 3i, which is very close to the root we calculated using approximate mode. So let me see how many iterations it requires. X dash after first iteration value will be minus 0.7309 plus 2.455i x dash after second iteration, it will give minus 0.5237 plus 2.314i, third iteration minus 0.4857 plus 2.334i, fourth iteration x dash equals to minus 0.4857 plus 2.3348. Now since the roots are repeating, we can see that this will be the root of the equation. So you can see the closer I will be with the approximate root or initial value I put close to your approximate mode, then number of iterations required will be less. So finally, this is the simplest method, or you can say this is the least troublesome method you can use to derive the root of nth order polynomial. There are other ways you can approximate this by using a since you know this is for lateral dynamics, you can use two first order equations and one second order equation, then you can equate the coefficient, but it is very lengthy, plus you will get, when you will get the solution, that will also become a fourth order equation, so you won't reach anywhere. So this is a better method to calculate a root of any nth order polynomial. And one thing more, as I told you that this, since this is for one root, now as you know that complex roots are in pairs, which will be mirror images about x-axis. So this will be somewhere about minus 4 point something here, then another root will be just mirror image of it about x-axis, which you can get, just replace this initial value with minus 1 minus 3i, you will get another solution with same number of iterations, it will be minus 0.04857 minus 0.4 with minus 334i. So this is the method to calculate characteristic of nth order, and more the numerical you will do, it will be clear to you, and that was my point of discussing this numerical to you. Thank you.